Hey, Wheaton North, Mr. Yergler here. Let's talk about gas calculations. So there's a couple formulas that we'll use. We'll go over those real quick and then get a few practice problems in. Let's get started. First, let's talk about the gas variables. So there's a couple of variables that affect all gases, and they are pressure. With pressure, there's several different units that we can use. Most commonly, you'll see atmospheres, sometimes kilopascals, sometimes torr. Millimeters of mercury is more of an older unit, but it's the same thing as torr, and so it's always just 760. So these are all equal to each other. You could actually also have psi, pounds per square inch, is a pressure as well. So on occasion, you'll have to do conversions between these. The next one is volume, which is always going to be in liters pretty much for all of our calculations. So if it's in milliliters, you'll need to make that conversion to liters. Moles is always just moles. The unit is moles. Temperature is a big one. Temperature is where everyone makes a mistake. So I would highlight this. Every temperature always has to be in Kelvin. Okay. To convert from Celsius to Kelvin, just add to 273. And then there's also a universal gas constant, and the universal gas constant is represented by R, and there's a couple different ones. It depends on your units. So 8.314, a joule is actually a liter kilopascal, and so if your pressure's in kilopascals, you'll need to use the 8.314. So you kind of connect those two, right? When you see kilopascals, this will be the R, the value that you use. If your pressure's in torr, then you'll use this one. If your pressure's in atmospheres, then you'll use this one. All right, let's look first at static conditions. That means that nothing's changing. We're not changing any pressures or any temperatures or anything like that. This is where we're going to use the ideal gas law. And this is a conversion that you've seen before, 22.4 liters per mole, and that's only at STP. Really emphasize this. Only at standard temperature and pressure is 1 mole equal to 22.4. I see a lot of people often trying to use this conversion when you're not at STP, and even sometimes when we're not even talking about gases. This is the volume of a gas at STP, 1 mole of gas at STP. So you obviously can't use this conversion for like solids and liquids and even gases that aren't at STP. Remember, the STP is standard temperature and pressure, so that's 0 degrees Celsius, which is going to be 273 Kelvin, and 760 millimeters mercury, 1 atmosphere, right? Any other situation with gases, you're going to have to use the ideal gas law, sometimes referred to as PVNERT. PV, pressure volume, equals moles times the gas constant times temperature. All right, let's look at an example. Let's say you have a container, a 25 milliliter container filled with 25 degrees argon gas at a pressure of 1.4 atmospheres. Calculate the number of moles that are present in that sample. At this point, it's pretty simple math. You just kind of plug into the formula and go. Our unknown is our moles. The R is not given in the problem, but it's always a constant. It's always the same. You can save yourself from making a lot of mistakes if you actually solve for the variable before you plug any numbers in. A lot of people want to just start throwing numbers into the formula, but actually take a second and solve for the variable that you're looking for, students actually end up making fewer calculation mistakes when they have the variable that they're interested in on one side and all the other variables on the other side. So we can adjust this formula solving for n by saying that n is equal to pressure and volume over R and T. Once you have that, now you can just plug your numbers in. 1.4. Make sure you make that liter conversion. Remember that the units on the R value is in liters. And I'm choosing the R value 0.0821 because my pressure is in atmospheres. Again, also make sure your temperature is always in Kelvin. This is where people make all their mistakes, is they forget to convert one of those units. So take the extra 5 seconds and write out the units so that you can verify, so that you can catch yourself if you're making the mistake, to make sure that the units match up. Comes out to 1.4 times 10 to the negative third moles, and if you take that times the molar mass, would be 0.0057 grams. Now let's look if conditions are changing. We can still use the ideal gas law, but we have to manipulate it to produce a useful formula. So this is actually all the variations of the ideal gas law, and there's actually more than even this. Let's look at these first two, for example. So here's our ideal gas law. Let's say, hypothetically, that moles and temperature are not changing. We're only going to change our pressure and volume, so we're looking at our pressure-volume relationship. If moles and temperature are not changing, and R is never going to change as well because it's a constant, then your pressure and volume is equal to this. This is basically becomes a constant because these aren't changing, right? And the ideal gas law works for any gas. So it's going to work at your initial conditions, and it's going to work at your final conditions. Both your initial pressure and volume and your final pressure volume are going to be equal to your moles gas constant and temperature. So essentially what this becomes is your initial conditions equal your final conditions, leaving out all the variables that are remaining constant. This is what's commonly referred to as the combined gas law. This is considering all of the variables changing, and if there's not a variable changing, like in the last example, then you would just leave those variables out. So this might be a helpful one to have written down. Anytime there's changing conditions, anytime you're given multiple pressures or multiple temperatures or something like that, you can use something like this. Let's look at a few examples. So constant volume. If the volume is constant, then that means the pressure and temperature must be changing, or the number of moles. In this picture, it looks like the number of moles is staying the same. That's not really what we're changing. What we're changing is the temperature, and we can tell that by the particle motion that's represented in the particle picture. So in this case, looking at our combined gas law, our volume is not changing, nor is our moles changing, and so the relationship essentially becomes pressure over temperature. If we look at this one here, now our temperature is remaining constant, and I really like this particle picture because it's kind of showing how the pressure is being changed. If you look at the big view, what we're changing is the volume. We're compressing this cylinder, and so that it minimizes the space between the particles, and the less space you have, the more collisions you're going to have with the surface of your container, and those collisions are what result in the pressure. And so in a situation like this, our volume is changing. There's no indication that our temperature is changing. Our pressure is going to be changing as well because we're increasing the number of collisions here. And so your gas law essentially becomes the relationship between volume and pressure, which is that first one. Let's look at an example where our conditions are changing. So the same kind of situation, 25 milliliter rigid container filled with our argon gas at the same pressure, but now we're going to change the temperature. We're going to heat it up to 50 degrees. So we're going to double the temperature. How much does the pressure increase? You may be tempted to say that it's going to double, but remember that our temperature is always in Kelvin. So let's actually go ahead and figure this out. Pressure is increasing and temperature is increasing, right? So volume is staying the same. Notice that it says it's a rigid container, so the volume won't change. So volume, number of moles, there's no indication that that's changing either, and our constant is always going to be the same. So let's put all of our changing variables on one side and all of our constant variables on the other side. So that essentially means moving volume over here and moving T over to the left side. So we end up with P over T equals NR over V. Now, like I said earlier, if this is going to work for our initial conditions, it's also going to work for our final conditions because the ideal gas law works for every gas. And so our NR over V is going to also be equal to our final pressure over our final temperature. So cut out the middleman. Essentially what you end up with is your initial conditions is equal to your final conditions. This is essentially the same thing as the combined gas law with the N and the V removed because they're not changing. Now we can just go ahead and plug in our numbers. Our unknown is our final pressure, and so that's in atmospheres. Notice that I've changed the temperatures to Kelvin. You get a very different answer if you don't change the numbers to Kelvin. Solve for your variable and you end up with 1.5 atmospheres. So that increase of 25 degrees actually only slightly increases the pressure. So this is just a couple quick examples. We'll get more practice in class. You'll see the ideal gas law a lot, and so it's very helpful to get familiar with it and get a lot of repetition with it. All right, this is Mr. Yerler signing off.